Okay, in this lesson we're going to talk about exponential and logistic functions. So after this lesson is done, you should be able to recognize the difference between exponential growth and decay. Given 2 points of an exponential function, one being the y-intercept, should be able to come up with the equation. You should be able to identify and define the number e. Use transformations to graph exponential functions. You guys should already be able to do that from Unit 1. We're going to talk about logistic growth functions when they're appropriate, what the equation looks like, and using logistic growth models to solve problems and answer questions. So, last unit we talked about polynomial and rational functions. In polynomial, rational, linear functions, x is always in the base of the expression of that function. What makes a function an exponential function is that the x variable, the independent variable, is now in the exponent, or is part of the exponent of an expression. So our exponential expressions will be written in the form of f of x equals a times b to the x, where a is not equal to 0 and a is the initial value. Okay, and what we mean by initial value, it's the value when x equals 0. Okay, so we talked about this in Unit 1, but they are growth when b is bigger than 1, and decay if b is between 0 and 1. Okay, so let's say you're given a graph and 2 points on that graph. We want to come up with a formula or an equation for the function shown. Okay, so we're going to start off with our exponential form, a times b to the x. And the first thing I see is that my y-intercept is given to me. It's 0, 2. So that 2 is our initial value. So when x equals 0, the initial value of this function is 2. So I'm going to plug that into our a value. Okay, so one less variable. Now we're working with our f of x equals 2 times b to the x. Okay, so now we're going to use the second point. Now remember, for any coordinate point, we've got an x and a y coordinate. So let's take and let's use that 2 and 6 and plug them in for our x and our y. So remember, this f of x can be replaced with a y. So now we can substitute in our 6 for our y and our 2 for our x. And when we do that, now we've only got this one variable in this equation, the b, so we can solve for the b. So I'm going to divide both sides by 2. Now we've got b squared. We just want b, so let's square root both sides. So b equals plus or minus root 3. So normally we would leave it like that, but since we're given the graph of this function, we can tell that this is a growth equation. So we really don't need the plus or minus. We just need the plus part. So I'm going to get rid of that minus, okay, and the plus. So our b is root 3. So let's go back in and put it all together. The function, the equation of this function is 2 times root 3 raised to the x power. Okay, so example 2. says describe how to transform the graph of f of x equals 3 to the x into the graph of g of x equals 3 to the x plus 2 minus 1. Okay, so using what we learned about transformations in Unit 1, this is our parent function here. So let's see which transformations we did to g of x. So the first thing I see is this plus 2 that's directly affecting the x. Okay, so since that x is in the exponent and we're adding 2 to that, that's going to be a horizontal shift to the left 2 units. That's our c value. So horizontal shift left 2 units. Okay, and then this minus 1 on the end is a vertical shift that's going to slide us down 1 unit. Okay, those are the only 2 transformations. So shift left 2, down 1 from f of x to g of x. So we can graph exponentials using transformations as well. In example 3, we're given g of x is 3 to the negative x. So since exponentials are going to have a variety of different bases, then from whatever function we're given, we're going to assume that our b base is from our parent function. So I'm going to assume that my parent function is y equals 3 to the x. And I'm going to go ahead and graph that. Okay, so 3 to the x is increasing. It's going to have a y-intercept of 1. And if we plug in 1 to this function, it's going to have the point 3,1. No, excuse me, it's going to have the point 1,3. Let's switch the x and the y around. That makes more sense. Okay, so this is 3, this is 1. Okay, so we've got 2 points. We've got our y-intercept of 1 and the point 1,3. So then we can kind of sketch from there. It's got a sharp increase rate of change. And let's not forget our y-intercept, or excuse me, our horizontal axis. Our horizontal asymptote. Let's get our words right. Let's make that a little skinnier. There we go. So horizontal asymptote goes along our x-axis at y equals 0, and we've got our function there. Okay, so now if we want to go from 3 to the x to 3 to the negative x, so that negative in there is directly affecting our x, so that's going to be a reflection over the y-axis. So our new function, if we do that in blue, so g of x is in blue, if you can just imagine that we're going to reflect over the y-axis. So this point 1,3 is going to become negative 1,3. Our y-intercept is going to stay the same, and it's going to become decreasing. Let's make sure we go through that point. And getting closer and closer to our x-axis. Okay, so there's our g of x. And let's make sure that we label our parent function. Okay, so final function in blue. Now notice if you have any function to the negative power, that's the same thing as if you have y equals 1 over 3 to the x. So remember that negative exponent takes the reciprocal of that base. So 1 over 3 is decreasing, and this is the exact same graph, 1 over 3 to the x as 3 to the negative x. They're equivalent equations. Okay, let's look at b. G of x equals negative 3 to the x plus 2. Again, let's start with our parent function. Might cheat a little bit and grab these two. Save some time. Alright, so we've got our y-intercept at 0, 1. We've got a point at 1, 3. So this negative here, if we go from our transformations from left to right, this negative is going to reflect us over that y-axis. So again, I might cheat a little bit. Take this and literally reflect it over our x-axis, our x-axis, and then we want to shift it up 2. So we want to take each of those points and we want to shift this point, which was 0, 1, which was now 0, negative 1, and shift that up 2, so that goes back to 0, 1, and then the point that was 1, 3, when it was reflected, became 1, negative 3. That point gets shifted up 2 units, so now it's at 1, negative 1. And our horizontal asymptote also gets shifted up 2 units. So if this is y equals 2, then our asymptote looks something like that. And our function in purple goes through 0, 1, through 1, negative 1, and looks like so. Okay, so final function g of x in purple. Graphing exponentials using transformations. Okay, the number e. You're going to see e a lot when we talk about exponentials, logs, and logistical functions. The number e. Many exponential functions in the real world, ones that grow or decay on a continuous basis, the key word there is continuous, are modeled using the base of e. Okay, just like pi is approximately 3.14, e is also an irrational constant, approximately 2.718. Okay, there is a definition for e. Just like pi is circumference of a circle over the diameter, e has a kind of a more complicated definition, and its definition is a limit. So as x gets bigger and bigger and bigger towards infinity, then 1 plus 1 over x to the x power approaches the value of e. Okay, you can test that in your calculator. If you put this into y1 and then either look at your table or keep tracing out larger and larger values, or keep plugging in bigger and bigger and bigger values, you'll get closer and closer to actual e. Okay, so let's look at another type of function, our logistic growth functions. Logistic growth functions take an exponential function and puts an upper limit on it. So whereas a normal exponential function is only has a lower bound or a bound below, a logistic growth function is bounded both above and below. Okay, and we can normally see two different forms of our logistic functions. I'm going to write them above here because I've got a little bit more space. Okay, one, we've got c in the numerator of a fraction, and in the denominator we've got 1 plus a times b to the x. Or when we're using our e constant, we may see it written like so, where e is the base and we have this k constant up in our exponent along with the x. Okay, so those can go in these two blanks. And that c on top of each of those fractions is the limit to growth. It's going to tell us the kind of our maximum of how much that this function can grow. It's not going to get any bigger than whatever that numerator is. So for example, if we had a application in biology where we're growing I don't know, spores in a jar, and there was some sort of limit on the food or the oxygen, the number of spores that could survive with that amount of oxygen, then that number would be the upper limit, would be that C value. Okay, so the graph of a logistic function starts off looking like exponential, but then it levels off. So instead of just having that lower bound, that bound below, that horizontal asymptote at 0, it's also got a second horizontal asymptote above it. Alright, so two horizontal asymptotes, one at y equals 0, and then that upper bound C, y equals C, is our other horizontal asymptote. Alright, so example 4 says the number of students infected with flu after T days at Springfield High School is modeled by the following function. Okay, so given P of T, we want to answer a couple questions. They give us a graph, that's nice. If we didn't have a graph given to us, we could plug this into our graphing calculator, make sure that when you do that, that you put this whole denominator in parentheses, and that you also put this numerator and, or excuse me, this exponent in parentheses as well. Okay, be real careful when you're putting exponentials in your calculator that you put everything in the exponent in parentheses. Okay, so what was the initial number of infected students at T equals 0? So T is our independent variable, that's kind of our X in this case. So on our graph, that's going to be our y-intercept. We could do this graphically or we could do it algebraically. So if we plug in 0 into our T, let's see what we get. So P of 0, 1600s on top, and we get 1 plus 99 e to the negative 0.4 times 0. Okay, so anything times 0 is 0, and any base raised to the 0 power is 1, so we've really got 1600 over 1 plus 99 times 1, which is just 99. 1 and 99 is 100, so we've got 1600 over 100. If we simplify that, then we've got 16. So initially 16 students infected. So this is a little different from our exponential functions. We can't just take our coefficient of our base. Okay, so notice this is kind of the exponential part of our logistic. We can't just take that 99 as our initial. We got to plug in 0 into T. Okay, part B. After 5 days, how many students will be infected? So now instead of T being 0, we've got T equals 5. So let's evaluate our function at P of 5. On our graph, let's see, if this is 10, 5 is going to be about halfway in between. Each of these tick marks on our y-axis are 100, so I'm going to say a little over 100. I would plug this into my calculator. We don't want to just guess. So plug this in your calculator. You can trace, or you can use your table, or on your home screen. If this is in y1, then you can do y1 of 5. Okay, so plugging that in, we should get 111 and some change. So after 5 days, approximately 111 students will be infected. Alright, part C, what is the maximum number of students that will be infected? The max, that's our upper bound. So remember, our upper bound comes from our C value. Our C value is on top of our function. So 1600 is our maximum number of students. That's also our second horizontal asymptote here. Ooh, make sure that's above. 1600. Alright, according to this model, when will the number of students infected be 800? Okay, so interesting. So they give us students this time instead of a time. So at 800, here's 800 on our y-axis. So we're looking for this x value. So it looks bigger than 10, less than 20 or 15 even. Looks like 11 or 12. So I would go to your graphing calculator and maybe in y2 plug in 800. So that'll give you the horizontal line, y equals 800. Find that intersection point, or you can go to your table and ask for that, plug in the y, ask for the x value, and you should get after 11 days. It'll be 11 and some change. So after 11 days, 800 students will be infected. Alright, last thing, let's look at the graphs of a logistic function. So in example 5, part A, we're given this function f of x. We're asked to find the y-intercept and any horizontal asymptotes. Okay, y-intercept, horizontal asymptotes. So I'm going to go ahead and get us started here. So our y-intercept, remember, is going to be the point 0 comma something, and our horizontal asymptotes are always going to be in the form y equals. And remember, we're always going to have two of them when we have our logistic function. One of them is going to be y equals 0. The other horizontal asymptote is going to be y equals our c value. So our c is 9 in this case. So there's our two horizontal asymptotes. I'm going to go ahead and graph those. Okay, so we've got y equals 0 and y equals 9. And let's find where our y-intercept is. So remember, our y-intercept is where x equals 0. So let's plug in 0. Let's do f of 0. Okay, so we've got 9 over 1 plus 2 times 0.6 to the 0 power. Okay, the more of these we do, the more that we're going to see that our base raised to the 0 is 1. So we're really just doing 9 over 1 plus 2, which is 9/3, which simplifies to 3. So that is our y-intercept if we wanted to graph it. This is 9, this is 0, so 3 would be somewhere in there. There's our point. We've got our upper and our lower bound, so our function looks exponential here and then starts to level off there. Okay, part B. Here is the equation for part B. Go ahead and do that in your notes, and we'll talk about that in class tomorrow. So exponential and logistic functions, from the equations to the graphs. We talked about the letter E. Make sure you know where E comes from, and be able to solve problems using exponential and logistic equations.